Linear search. There are two jobs that computers do, and nearly everything degenerates into these two jobs. One of them is searching for information. The other is sorting information. Okay? Everything degenerates into that. So when it comes to searching, we want it to be quick. We've got two methods, linear search and binary search. Unfortunately, there is always prerequisites for a search thing to happen. So for linear search, one of its advantages is data can be in any order. We don't need to know anything about the data. Okay. We start with the first piece of information. So whenever you're describing an algorithm, there are like three things that you need to be able to explain. How does it start? What goes on? And when does it end? When does it stop? Okay. So you start with first piece of information. Now, I'm recording this, but also there's a Craig and Dave video on this as well. So in my mind, what I would do is I would look at my stuff, look at Craig and Dave's stuff, but I'd also look at other stuff. So you can get a real good round. Everyone has their own little nuances and things that they bring to it. You're trying to like get the best knowledge from everybody. Okay, so no one perfect description of anything. Okay, so we start with the first piece of data. We then, it's called linear search. So we just go in sequence. So we just go to the next. So then the process of it is just to go, right, move through the data set. So this is going to be a list. So I'll just looking for what we're searching for. When do you think we stop? Just think logically about it. You're looking for something. Just think about how you might search for something. Go on, Ennis. Right. When we find it, so we go, yes, got that thing. Found that number or whatever it was. So yeah, once you found something, you don't go, oh, I'll continue searching. No, don't think so. Is that it? When else might we stop? Yeah, go on. Yeah, it might be that the thing doesn't exist that we're looking for. So actually, we're going to exhaust the list. So we will get to the end of the list. So when we found, we stop, or if at end of list. Which meant, oh, it wasn't in there, not found. You'd be a really, really, really poor program that assumed that the thing you were looking for existed. Can you imagine if you do like a search on a hard drive for that file that you called document 3 and you didn't think where you saved it, and Windows went, I'm going to assume it exists, so I'm never going to stop. I'm going to make it my mission to find that file. No, that'd be bad. Right, so let's have a look what this might look like. So generally when we talk about lists of data, we tend to do this. We create a list like this, and we just like go, oh, okay. Make a list. So this is my data. Now, in the computer, we can represent a list using something called an array. Okay, where we have a name, which is this. That's the name of the array. And then we have locations within that array, starting at position 0. And then in those locations, we put our data. So let's have some alphabetic names. So I'm going to have soup. I'm going to have chicken. I'm going to have cheese. And I'm going to have mango. Right. Now, looking at this data, if we was to think alphabetically, is it in alphabetical order? No. Soup shouldn't come before. What would the actual order be if it was alphabetical? Very good. How did you do that? Because that's quite interesting. Right, what if I'd have had these two? If I'd have had these two words. Why? Right, D comes for X. But in a computer, how do we represent those letters? As numbers, correct. We do, don't we? Which we call, there's a couple of different methods. Well, there's lots of different methods. What are the two methods that we know for storing character data? Nope. Go for it, Dominion. ASCII is one way. What's the other way that we actually use? Unicode. Right. So because those characters actually are represented by numbers, when we're comparing text, we're not comparing text, we're comparing the numbers that represent those characters. What if I had this? Which one comes first? AAB? How many are going for the AAB? Oh, a lot of dumbasses in the room. Right, it is the bottom one, but why? Yeah, uppercase letters have got a smaller number than lowercase letters, which sort of like sounds the wrong way round. Capital A is actually in ASCII 65, little a is 97. These things matter. These things, as you're a programmer, matter. That's why programs can be case sensitive, because the letters are different numbers. Okay, and you know, it's only people who understand these things that really understand sort orders for text. Okay, so that's just a little side thing. So let's just rub all that out. Right. Okay, so the linear search process. Right, so I said start with the first piece of data. So which location in this list am I going to start at? Soup. Position 0. So I'm going to look here. Right, we need something to search for. So I'm going to search for avocado. So I'm going to search for avocado. Which I can't probably spell. He's probably don't spell it like that. Avocado. Avocado. Go on. Is that how you spell it? It doesn't look right. Not to me anyway. Too many A's. Right. Okay. So I am going to start at position 0. So that's my start point. So all I'm going to say is, like, I'm looking for avocado. Is that the same as the item at position 0? And I'm going to say, no. So I'm going to move on. The reason this is called linear search is because you just go in sequence. You just go like, start there, just move along. So I'm now going to look at position 1. And I'm going to say, right, avocado. Is it chicken? Yeah, I don't know. I don't know. I don't even know what an avocado tastes like. But that's a no from me. I don't know. It depends. It's a fruit, isn't it? So I don't know. It depends if you like fruit. Right. So I move along and I go, right, I'm now at position 2. Now, can anyone tell me what mathematical process I'm using to move to the next thing? So if I start at 0, how do I get to 1? Go, Toby. Yeah. I'm doing what we call in computer science terms incrementing. I'm incrementing by 1. CPUs can do this really quick. They have instructions to do it. Okay, all built in. It's what they're designed to do, process lists of data. So we look at position 2 and we go, oh, blimey. No, it's not. It's not what I want. So I move along. So I increment. But I don't care what they actually physically are like. I'm just looking at their names. Okay, so I'm looking at their names. So I'm going, avocado is not the same as mango. Now, here's the key bit. So we move on and we're looking at what position would we be looking at? 4. So that is 4, but there isn't a position 4. There are 4 items, but we started at 0. We always start at 0 when we're numbering things in computer science. So what we're actually doing, we found our stop condition. We didn't find what we're looking for, but we got to the end of the list. How many items are in this list? 4. So if the position we're looking at is the same number, I'm trying to like give you the algorithm without worrying about the code too much, but I want you to think about this. So we're saying like, okay, if I'm trying to look at a position number which is equal to the number of items we got, then we've got to the end. We've gone past the end of the list. And that's it, and we stop. Okay? Let's just do one more where we actually find something. So let's, just for speed, let's go for soup. Bearing in mind, you lot could tell me straight away, instantly, that avocado wasn't in that list. How was you able to do that? You can see it. When we're programming, we generally can only see one item at a time. Unless you were using some sort of parallel processing system, which you can do. All right, but in general, we can only look at one item at a time. We as humans are really good at taking in vast amounts of simultaneous data. Okay, but you can't write algorithms like that. Algorithms have to be all in that dummy steps, really. Yes, Aaron. Yes. Unless we specifically wrote our code to say we don't care about case. But we'll look at that when we start looking at some string tasks and things. But yeah, so in general, case does matter because of ASCII and Unicode. Okay, so let's have a go at looking for soup. So I'm going to search for soup. No, you're only searching for a single item though. So you can't search for multiple items. It would be multiple searches. Right, okay, so I'm going to start here at position 0. Now, the reason I picked this one is because it's important. Right, I do a search and I say, oh, hang on a minute. The thing at the first place is soup. Let's stop. There is no quicker search than finding the first thing that you were looking for. All right, that's important. When we come back to binary search, when we do that next time, it's one of the advantages of linear search, but we'll come back to that. So keep that in your head. If the first time you look at is what you were looking for, you didn't do any work. So it was like, bang, instant, found it. You know that thing when you're looking for something and you like go, you know what, I'm going to start at the back, and then you find out it was near the front. Or if you look at the front, it's the very last thing you find, and you think, oh, God, if I'd have gone the other way. But yeah. Right, so we've got 2 stop conditions, finding it and not finding it. These sort of logical thought processes are what make us have the ability to create the algorithm to solve a problem. That's one of the things we've got to spend this year working on. Okay, I know some of you aren't very confident about this, but actually it is a little bit like Lego. Once you've got the basic building blocks, you can construct complicated things. And at GCSE, they're not going to ask you to create Flappy Bird in the exam. They're not. They're not. Okay. What we might do as a class, though, is we might create Flappy Bird. Just have a look at how it works. It's not hard to write. You can write it in 5 minutes. Yeah, it's not hard. Right, okay, I'll stop that.